Hello everyone, Mr. John here with a quick practice problem from this year's AMC 10 practice exam on the online competition system. Let's take a look at this question here. In an avoidant coloring of a rectangular grid, each small square is either black or white, and no two adjacent squares, so adjacent means they share an edge, are black, both of them being black. So we see our kind of grid here in this case, and we see an example coloring that is okay, right? So this is a good coloring. This is a avoidant coloring of this grid because none of those black squares are adjacent to each other. For example, if this square here was also black, then these two would be adjacent and that would be bad. So this is a good example, and we can of course have bad examples where things are adjacent to each other there as well. Now our question is how many avoidant colorings there are of a 4x3 grid, right? And so this problem is from this practice AMC 10 test that is available for students on this year's the 2021-22 contest portal that you use to take the online version of the exam. But this is an interesting problem that I want to look at here and talk about too. Okay, let's jump then into some space where we have a little bit of room to work. Remember, avoidant means we can't have two adjacent black squares, and we want to figure out how many avoidant colorings there are in this 4x3 grid. Now, we're going to look at a couple of cases here. And there's different ways to break this down, but I think a natural place to start is to think of these center squares as special, right? So if we think of these two center squares in both cases as kind of special here. And there's a couple of things that can happen in these center squares. So let's consider here a first case. And right, I want to kind of put off right off the bat before we kind of continue anything here, we have a 2 times. This case can appear in 2 different ways. Pretty obvious the 2 ways they're going to be appearing in, but this is going to be if we have one black square in the center. So suppose this top square is black. The times 2 comes from, of course, it could be the bottom square. But then everything is mirrored, so I want to have that 2 times right off the bat so we can just keep track of whatever there is for this case, we're going to multiply it by 2 to deal with the fact that there's kind of double ways to deal with this there. So once we know that black square where one of them is in the center, right, the other square has to be white. And so this is where, right, we can flip it, but also that there's really some things we can start saying about the rest of the squares if we have the center square kind of in that way there. So we have to have 4 whites on the kind of north, south, east, and west sides of this black square. Now, this divides up the rectangle into some regions from there. And this kind of is the key observation, the key way we're going to be thinking about solving this problem. So, first of all, we have 2 squares here at the top. Let me label these with question marks for now. And the question mark here means that those can be kind of whatever. Those don't have any adjacent squares that are black. They don't have any effect on each other. So they can just be white or black in total. So we have 2 squared ways for those 2 question marks we have there. Now, here's going to be the big idea or the big kind of preview of what's coming for the rest of this problem here. So now we have these 5 squares left on the bottom. Now, what do we notice about them? Every one of those squares is adjacent to another square in that case, but there's no kind of multiple adjacencies, right? Every square has, right, one on either side of it, right? The ones in the middle have kind of left and rights of them. But we can kind of fold this down. This is basically arranging these 5 squares in a line. So I want to write it here as times L5. And let me kind of define what I mean by L in this case here. My kind of L of n, so if we have L of n, this is going to be the number of ways for n squares in a line. And so this again will be kind of avoidance colorings and stuff like that there, right? So this is now just going to be what happens, how many ways are there to do this if we just have a line in this case. So, right, we can fold it down. This is the same as putting those 5 in a line in this scenario. Now, we could of course just hammer that out now, but I want to look at our second case and I want to explain why this is going to give us that kind of pattern there, and we can kind of look at it that way as well, and this will be helpful as a kind of general method here. So our second case, right, you could call it case 2, or maybe let me call it kind of case 0, just to match that this is going to be 0 black squares in the center. And so then we have kind of 2 white squares in this scenario there. Now, there's a circle on the outside now. So we don't quite have a line, but we have this circular ring around the outside there. Now we can split this into 2 cases as well, but let's kind of look at the upper left. You could look at any square here, but what happens if this square is black? Well, just as before, we have 2 white squares adjacent to it. Now, what are we left with? Here's where we're going to start seeing the L come into play again. Notice we have this ring of squares. It's like a little J here, but it's again could be folded down into a line. And how many pieces of this line are there? How many squares are in this line in this case? There are 7 of them. So we could look at this as L7 to start. But that upper square doesn't have to be black, right? There could be a white in that upper region there. So if I erase all of these here, let me put the white in that upper left square there. But again, when we have the white up there now, we now still have a line. We have almost a full circle, but because we know it's white in that upper region, we now don't have any, right, circular things to worry about, right? When stuff is going around in a circle, then, right, the first relates to the second, third, fourth, fifth, but then when it circles around, that's where you come into some problems. That's where you have some issues. But by looking at it this way, we can break it down into 2 different cases. If it's black, we go to a line with 7 squares. If it's white, we reduce it to a line with 9 squares in this case. And so now we can start thinking about, okay, what happens in a line in this scenario? So let's look at a couple of examples to start with a line, right? So if we have L1 in this case, L1 is pretty clearly 2, right? If we just have one single square there, right, there are 2 choices for it and we're good. If we have 2 squares there in this case, well, they can either be white or black for both, except we have one scenario that's bad, right? Black, black is a bad scenario, and that's the only scenario that's bad. So if we have a L2 here, this is going to be 3. 4 minus 1, there are 3 outcomes in that case there. So what does this allow us to do then for the problem? Now let's think about there being more squares. So we're going to kind of jump to a general scenario here. All right, so let me draw out the first square and the second square, and then kind of a dot, dot, dot in this case there. The reason for this is we can now come up with some sort of recurrence in this case. So in general, right, let me not write it down, but of course I mean now for n at least 3, let's think kind of like the bottom case where, okay, that first square, this first square could be white. Now, if that first square is white, does it affect any of the later squares? Does it affect anything that's coming after that? No. So that's going to give us a Ln-1 in this case. So we have kind of a L-1 as that scenario there. So let me move this over, give us a little bit more room here. And right, what about the other scenario? What happens if we have a black square first? Well, if we have a black square first, then we know we have to have a white square second. And how many squares are left now? Now we have n-2. And once we get that white square, we're like starting over. So at that point, any avoidant line of squares with n-2 squares would work. So that gives us this following recursion. In general, it follows this Fibonacci sequence type pattern, right? We add up the other terms there, and the previous two terms add up to be giving us the next one. So this is a pretty nice pattern now, right? This allows us to find L3, right? This is 2 plus 3 is 5. We can do L4, 3 plus 5 is 8, right? And so you can start calculating these and working your way up pretty quickly, right? So we have L5 is 13, L6 is 21, right? Then they start getting a little bit bigger from there, but L7 is going to be 34. L8, right, is then going to be 55 in this case. And L9 is 89. You could keep going though, right? This pattern doesn't ever need to stop. You could calculate however many of these Fibonacci numbers you need in this case. But notice these are exactly what we need for our problem. So going back to case 1 now, we have 2 times 4 times L5, which we said was 13. So 2 times 4 times 13, 8 times 13, we are going to get 104 for that scenario. What about the second case? We said that was either 7 squares in a line, so that's L7, which is 34, or L9, which is 89, 9 squares in a row. So we have L7 plus L9, 34 plus 89 is 123. And we don't even need the multiple choices to help us here. Our final answer is dependent on these two numbers, 104 and 103. So we take those and we get our sum, right? So if we look at the total number of avoidant filling colorings of this grid then, right? We have a 104 plus 123, and that gives us our final answer of 227. So 104 plus 123 is 227, and that is our answer. Right, you can check back that that was one of our answer choices, so we're okay in everything. And so 227 is our final answer there. Now, as a little bonus for this one, I want to show that this pattern can come up in other places. So I'm not going to solve this question, but this is another old AMC question on the 2015 exam, number 22 and 17 respectively on the 10A and 12A. Seemingly a totally different question. So 8 people are around a circular table. They each have a fair coin. They flip their coins. If they get heads, they stand up. If they get tails, they remain seated. what is the probability that no two adjacent people will stand? If you think about this a little bit, you will soon see that this question is very, very related to what we just did. Actually, this question should be quick to solve. You should be able to solve this in 30 seconds or a minute based on what we just did. We did actually all the calculations that you'll need in the previous practice question too. So, good one to practice a little bit more on as well. So, that will be good for today then, right? Just want to remind everybody that there's a lot of great resources on ZIML, right? Whether you're doing last minute preparation for the AMC 10 and 12 or doing preparation well in advance, there's a lot of great things there to check out. Check it out either at ziml.areteem.org or with the mobile app. Also, if you liked this video, please subscribe to this YouTube channel, hit the like button. Really helps us out, and I hope to see everybody in the future for more problems as well. Goodbye.